Hello guys, what's up? Back with another circuit, delving into a bit of power electronics today. So what we're looking at is, as you can already see, the buck converter. It's one of the classic DC-DC converters, which is basically a DC chopper and LC filter. That's essentially what it is, and what it allows you to do is step down DC voltage. So essentially that is the buck converter, and you give your input voltage here. This is just a nice schematic which I found. You give the input voltage here. You have a switch here, which is the MOSFET. You need a flyback diode or freewheel diode, as they say. You have the inductor, and you need a capacitor, and yeah, whatever load you want to connect. So you give a higher input voltage here depending on the duty cycle of the gating pulses which you give at the switch. You're going to get an output which is lesser than the input. So that is how the buck converter works. If you want to delve into the equations and so, you're free to do so. So let's just get into the circuit what I use. So first of all, you could go the digital way and generate the gating signals from a MCU, and even perhaps do some closed loop, as they say, load regulation. Yeah, sorry. So basically, irrespective of the kind of load you connect, you would like your output voltage to be constant. So that is when you need closed loop. But today we'll just be looking at open loop, because closed loop comes with its own set of requirements. And so today let's just look at open loop, and we're going to manually control the duty cycle. So here we're not relying on the controller to do that, and there's no programming. Today we are going fully the analog way, as they say. I'll be using the TL494, which is a popular PWM IC. There's another one, I think it's called the UC3843, which is what I've tried and used for my boost converter. I'll probably get to that video someday later, but yeah, this TL494 is a nice one. It has two error amplifiers which could aid us in the closed loop, which I would be trying in the future. And anyway, as a PWM IC, it has the oscillator. It will generate the gating pulse which you need for your switch. Yeah, depending on whatever RNC values you choose, you can go through the data sheet. The formula is there. And then it even has this nice reference which it generates. So depending on what VCC you give, I think it's suggested that it's at least 10 volts or above. I'm not very, yeah. So from that, it's going to generate a fixed 5-volt reference, which you can then use as a fixed reference for your non-inverting input, for the error amplifiers, for the closed loop, as I said. And also another thing you can do is you can manually, in this case we want to manually control the duty cycle. So when you go, I'll just show you the circuit just in a bit, but basically when you control this 5 volt through a pot and you give it to this, let's just go to the pinout here. So if you give it to this DTC, which is the dead time control, you can vary the duty cycle of the gating pulse, and that's exactly what we want. So this first three, let us just leave it alone right now, we don't need them. This is the dead time control, this RTCT, those are the timing oscillator and resistor, capacitor and resistor, to choose your switching frequency. The ground is there, and then also it has two, as you can see here, it has two transistors, BJTs, and though they are in open collector configuration, so you basically pull these up, their collectors, to your VCC, and that's where you can take your output. And this IC, you can do both, as they say, the half bridge. You could drive a half bridge with this, since it has two, so that would be the dual mode or something, as they say. I'm not very quite sure, but yeah, you could drive a half bridge, but in this case we just want to drive a single switch. So in that case they call it the parallel mode. In that case both of them would have the same output, so we'll just take one of these transistors, pulled up to VCC, and we take the output from there and ground the emitter, and back to the, so you could, let's say, choose C2 and E2 or C1 and E1, and the VCC, yeah, whatever VCC you give. This output control is what decides if you want to drive two switches or just a single parallel mode, as they say. So in this case we'll just ground the output control. So there in the data sheet, you could, that would basically make it in the parallel mode, which is what we want to drive a single switch. This is that 5 volt reference which I was telling you about, and these are the two inputs for the second error amplifier. So let's leave that alone right now. Now jumping into the circuit, this is in Proteus. So first of all, we have the TL494 here. This is the timing oscillator which I've chosen. It's for around a 50 kilohertz switching, which is a moderate switching frequency. As you know, it's a trade-off between the inductor size and the EMI losses and so on. So you need to choose whatever according to your design. So I've chosen 50 kilohertz. This is the open collector output. I've pulled it up with 1K, and this VREF, you give it through a 1K pot in this case, and you give it to the dead time control, the wiper, and when you vary that wiper, you can get a control over the duty cycle. Rest of it, I'm not going to be connecting in any of the error amplifiers, and the control input is grounding, as I said, for the single parallel input. And that basically goes to our driver. And you would say, why do you need a driver? I mean, this thing already has a collector output, right, which can sync up to 200 milliampere, which is a nice good current but for the gate. But as you can see here in this circuit, if I go back, this output here is not actually with respect, so as they say, low side. This is on a high side. This switch is on a high side. It's not reference to ground. If you can see through this diode in one switching cycle, since this would be reverse biased, this would not be with respect to ground. And later, yes, it would essentially get forward biased and connect to ground. But whenever you're going to be driving this gate with respect to the source, you cannot ground reference this, because to reliably turn on power MOSFET, you at least need 10 volts or above. So where are you going to get those floating 10 volts, as they say? So that's when you would need a high side driver. So this is a popular IR2110. It's a high side and low side driver. You use it in full bridge and half bridge configurations. So yeah, this is as the data sheet says, this for a half bridge. But in this case, we don't really want the low side. I'm just concerned with the high side. So we can make use of this HO and VS, which is the floating supply. And I won't go into the details, but basically this provides a bootstrapped operation, as they say, and this is going to create a floating supply above your ground, because you need at least 10 volts or above, not with respect to ground but with respect to the gate and the source. So this bootstrap capacitor, when charged through this diode, is going to provide that voltage which we need to turn on the high side MOSFET. So these connections, I won't go into the details, but yeah, you can see we're giving the output of this pulse from the TL494 to the high input. And then we're taking the output from this H out. This is the bootstrap capacitor, 1 microfarad. I've just put two 470 nanofarads in parallel. And yeah, this is a Schottky diode. Nice, I think around 40 volt rated. It's the 1 in 5819. And yeah, it's for fast switching. It's great, low voltages. So yeah, you need that bootstrap diode for charging the capacitor in one direction during one cycle. So that is there, and we're going to be taking the output from the H out, and that H out is going to go to, this is, you could say, this is our control circuit, if you may say, and this is our power electronic circuit. Here I'm giving input of 12 volts, and that 12 volts is going to be constant throughout here. My IR2110 is also powered using the 12 volts, the TL494 also using the 12 volts, and we're going to be stepping down the 10 volts. So later I could maybe choose a different voltage, but just right now for simplified demonstration, we just take 12 volts. And yeah, that what I showed here, this PWM from the IR2110 is going to come to this gate, and 10 ohm series resistor to reduce the ringing and so on. So yeah, this here, and the source of it is connected to the bootstrap diode. Same, I'm using the Schottky diode from before, since anyway it's a low voltage, we are bucking it. And according to the calculation, which over here I used I think TI has an application note. I don't have the link open right now, but it has an application note on the buck converter design, so I used that mostly. And then yeah, maybe just derive a few formulas and get a basic for choosing the L and C values using your inductor current ripple and the output voltage ripple, choose whatever design you choose. So here I think I've taken 20% ripple and inductor current ripple and 1% voltage ripple, which is a modest amount. So 330 microhenry and 22 microfarads, and I'm putting a 50 ohm load that would draw about yeah, depending on, yeah, 5 volt output, it would draw 5 by 50, so 100 milliampere. And yeah, but now we're going to be doing the variable output, so it would draw different current. But this 50 ohm, just 200 ohms in parallel for increasing the power capability. I don't have a power resistor right now. I just have the 1 ohm right now, 10 watts. So yeah, we have to make do with this. So yeah, I hope the circuit seems fine. Let's go to the physical circuit now. So yeah, this is the physical circuit. Yeah, as usual, I know it looks messy, but if I do get around to maybe soldering this on a perf board or something, it would look better. But yeah, I just don't seem to have the time right now, so the breadboard is all I have. So yeah, this is the TL494. That's the IC over there. In the middle, we have the IR2110, the driver. That's the MOSFET. The inductor here, I'm using a drum type inductor. I do have a toroidal. I'll probably try that too. And yeah, this is the 200 ohms in parallel for the 50 ohm, and that's the 22 microfarad capacitor. That's the IRFZ44N standard power MOSFET right there. And yeah, let's look at the output voltage, and even let's see the waveform so we can compare how the output voltage is. So according to our design, basically we should be needing around a 46% duty cycle to step down 12 to 5 volts. So we could maybe even verify that. So let's just turn on this oscilloscope here, and yeah, I have my power supply here set to 12 volts, and as I said, everything is running off 12 volts, so that is fine. And yeah, here I got on a separate small breadboard here the pot with which we're going to be varying the duty cycle. So currently it's nothing is going on, it's 0. So let's start. Yeah, let me just start this here, and you can see we have around a 5 volt output. And let's just turn off the flash. Yeah, we have around a 48% duty cycle, which is quite close to our 46, so we verified that. And let me just vary this pot here, and you could see as I maybe decrease the duty cycle, let's say 26%, output has dropped further, it's become 2.9 volts. Maybe let's try even further, let's try to 13%, almost 1.5. So you can see the lesser you make your duty cycle, your output voltage is decreasing, so the buck action is more and more. Maybe now let's increase it a bit. Let's go back to 50. Yeah, around 50, that gives us the 5.2. Maybe let's try around 50, 60%, that is 6 volts. And now you can just see the voltmeter, I'm just turning the pot, it's increasing, so you can clearly see that the bucking action is happening quite well. And yeah, okay, I guess the resistor is heating a bit, so I'll probably have to switch off the circuit. But yeah, you could see clearly that depending on how you change the duty cycle, the output is clearly getting changed. So yeah, that was all. I'll just switch off the circuit, it's good, I can smell the resistor burning there. So yeah, but you could clearly see with the waveform, and even the output voltage, currently it's open loop, but yeah, we could the whole point was demonstrating the bucking action is working, and the gate pulses are doing fine, the high side drive is fine. And yeah, so I hope you like the demonstration. I'll probably come up with the closed loop one after doing a bit of a research and even studying a bit. But yeah, thank you for watching. Stay tuned.